This is Tom with Tom Cisco Labs. We're going to do a little lab here today. This is going to be just kind of fun. It's something I thought about. It's something I've done before in real life, but I think it's important to know how to do this and have this down. It's basically what we're going to be doing is we're going to create an IPSec tunnel between these two routers. Then we're going to create a GRE tunnel over that IPSec tunnel, and then we're going to advertise a couple of networks through OSPF. Just using OSPF area 0 here, this lab's not about routing, so we're going to keep it simple. But the reason I want to use a routing protocol there, like OSPF or any of them, is we're going to use multicast, and we want to have multicast between these routers, and OSPF requires multicast in order to send us link states and hellos and all that kind of stuff back and forth to each other. Advertise routing updates. So a traditional IPsec tunnel by itself can't handle multicast, but GRE will pass as multicast. Now GRE by itself won't do encryption, so it wouldn't be secure. So we have to do GRE over an encrypted tunnel. So I'll show you, I'll explain a little bit here about what we're going to do. We're just going to pretend like these serial interfaces that are connected. This is just a couple T1 cards with a crossover T1 cable between them. We're going to pretend like that's the internet right there with a couple of public addresses. This could be any two routers on the internet that are publicly routable to each other. You know, they can ping each other or whatever. And we're going to create a couple loopback interfaces here. Okay, these loopback interfaces are going to be the interesting traffic source and destination IP addresses for our IPsec tunnel. So we're going to use the public addresses for the peer IPs. However, we're going to tunnel traffic that's from this IP to this IP, and tunnel traffic the other way from this IP to this IP. And we're going to tunnel that through the IPsec tunnel. That's our IPsec tunnel IPs. Okay, we're going to create a couple other loopback interfaces, L22 and L11, and these are just going to be our test networks that we advertise into OSPF and make sure that the routes come across. And then we're going to create these two tunnel interfaces, and these interfaces are going to be for our GRE tunnel, and we're going to build our OSPF neighbor adjacency between these two tunnel IP addresses. So we'll have these GRE tunnel IP addresses will be our OSPF adjacency, with which we will advertise these networks into OSPF. These loopbacks will not be advertised into OSPF. These are simply here to identify interesting traffic for the tunnel. I like to keep my tunnel traffic on separate addresses. I don't like to have traffic going to the public IP here and to the public IP here be my interesting traffic. I just think it keeps things cleaner. So we're going to be using a couple of 2811 routers, version 12.424 GC5, and it looks like this guy's got the advanced IP services on it. That's router 1. We'll also be connected to these via the console port through a access server. And this has the same exact version, I think. I don't see the GC5 thing, but you know, close enough. So what we're going to go ahead and do is create our interfaces to start with, except for our tunnel interfaces. Those will come later. So we'll go back over here to router 1. Oh, I was on the wrong router too. That's why. That's a 2600. Alright, let's try port 9. Okay. So yeah, this is a 2800. This is 2811. 12.424 GC5 as well, advanced IP services. Okay, so we'll go back over here to router 1 and start setting up some interfaces. So we're going to go to interface S0/0/0. We're going to do an IP address of 209. I think I had that as 55.101.1. This is /30. Boom. We're going to do a no shut. We're going to do int L1. And this IP was 10.1.1.1. We're going to do a /32 on that one because we only need the one IP address for interesting tunnel traffic for our IPSec tunnel. Ooh, if I could type today. And we'll go ahead and make this one a class C address. Okay, so we'll go ahead and come back here, do a show IP interface brief. If I could spell brief. And we see we got our address there. It looks good. We've got our address there. It looks good. It looks good. It's exactly what we want. So we'll go ahead and go over here to router 2. We have that address. We'll do a no shut. We're going to do int L2. And we'll do the full /32 mask. And we'll go ahead and do 10. Oh, I did the wrong IP address on L2. Did I do that? Yeah. Let me fix that. Okay. Go ahead and double check. Show IP interface brief. And that looks good. That looks good. And that looks good. So now let's go ahead and see if we can ping between our publics. And we can. We're good. So what we'll go ahead and do now is we'll create a couple of routes. So I'll explain. What we would normally have probably is like some type of a default route or something on the router for it to be able to get to the internet. But in this case we don't. So we need to send traffic that's destined to L2's to the L2 loopback from router 1. So we need to send that to out the serial interface. And we're just going to send it to this remote IP address. And now those private addresses wouldn't in a real scenario be routable over the internet. The point isn't to route them over the internet, but once they hit this outside interface, when we build our crypto map, it's going to match the access list and become interesting traffic, and it's then going to be encrypted between these two IPSec peers. So we'll go ahead and create that route now. This is we're on router 1, so we got to go 10.1.1.1. This is /32, and then we're going to go to 209.101.1. Okay, and now we can go ahead and back there. And come back to router 1. And so this one, when we go to 10.2.2.2, with /32 mask, we want to go to 209.55.101.2. Okay, and since we're not on the public internet right now, we could ping these. It's just going to route them. So we could do ping 10.2.2.2 from a source of 10.1.2.1. And it works. If this was a real internet, those private addresses are not going to be routable over the internet. So you wouldn't be able to get this ping to work until after the IPSec tunnel was up. But that's good. We know our routes are working. It's sending it out the right way. So now we got to go ahead and build our IPSec tunnel. So we'll take a short break. I'll be right back, and we'll start building that IPSec tunnel. Okay, so we're back here, and what we're going to go ahead and do is start building our IPSec tunnel. So now we're going to build the tunnel that will tunnel traffic that is going between these L1 and L2 IP addresses. And it's going to tunnel it over these public interfaces. So we'll go in here. First, we're going to create our IPSec policy and do a we're in comp T. Crypto IPSec policy 10. You just have to give it a number. We're going to give it the number 10. Okay, so now we go in here and we look, and we want to set our authentication. And we'll set that to pre-share. And we're going to set our encryption to 3 des. And then we're going to set our group. And we'll just use the group 1. That's fine. And we'll set our hash. It should just be MD5, and SHA we'll use MD5. And we're going to go ahead and set our lifetime. Okay, it's just in seconds. So 86,400. And that's all we have to do there. We'll go ahead and exit back 1 level. And now we got to put in our pre-share key for our IPSec. And call it CCNP. How about that? An address. And this is going to be the peer IP address for this IPSec tunnel. And the peer IP address will be the outside IP address of the other router. So 209.55.101.2. Okay, now we're going to go crypto, IPSec, and we're going to go ahead and set our keep alive here. And we're going to go ahead and set to 1800. Okay, so now I'll go ahead and do a show run. And we'll take a look at this. So we see there's our encryption, our our hash, and our authentication type. Now it didn't show the Diffie-Hellman group, and some, if it's the default option, it won't show it there. And so here's our IPSec key, and here is our keep alive time. So we'll go ahead and do a show crypto ISA camp policy. Well, so here you see we set that one lifetime to 86,400, and then we set this keep alive to 1,800, and you might wonder what that's about. So the 86,400 is the lifetime of the association. There's no volume limit set. Now it'll make a new association when that runs out. The keep alive is every 1,800 seconds, and that's what's going to keep the tunnel active. Basically, it's going to stay alive even if there's no traffic for 1,800 seconds. And that's just for, IKE phase 1, which is ISA-Kemp, and then the IPSec, the phase 2 stuff. That's what we're going to define now. And so, what we'll probably go ahead and do first is make our access list. Call this secure traf, set traf. And so it's going to be from the host of 10.1.1.1, which is our loopback IP, and it's going to be to the host of 10.2.2.2. Okay, now we're going to apply this into our crypto map, and the way this works is says, hey, if there's traffic coming from 10.1.1.1 to 10.2.2.2, we're going to encrypt that. That's going to get tunneled. It also works in reverse. When the router receives a packet into that tunnel that's destined, that's an encrypted packet, it's going to verify that the packet is from 2.2.2.2 and to 10.1.1.1. So if we had other networks here that we wanted to encrypt through our IPSec tunnel, you could specify them here. And of course, there's an implicit deny at the end. So any packets that don't match that are going to get dropped. Now, that doesn't stop packets that are unencrypted, that you might have a NAT overload on that outside interface and use it for web access or whatever. It won't stop those packets. Only encrypted packets is it going to check the in reverse on this access list. And encrypted packets will have to come from 10.2.2.2 and to 10.1.1.1. And on the way out, if they come from 10.1.1.1 and they're destined to 10.2.2.2, then it will encrypt them and send them to the other end of the tunnel. Okay, so with that, we'll exit back one level. We'll do a crypto. And we're going to go to, I'm doing a couple IPSec things here. First, we're going to set up our transform set. And this is just, we're going to give it a name, and we'll call it CCMP. Just keep it simple. And I'm going to use AH here, because if you use the ESP, you got to do a couple extra little things to make that work. In real life, you probably want to use ESP, and you'll have to set up your ESP keys and stuff. But here, we're just going to use AH. We're all good there. And so now we have to set a setting under this transform set. And we're going to set the mode. And I was going to do a question mark. There we go. And we can set it to do payload encapsulation, which is not what we want to do. We want to do datagram encapsulation, and that's going to be the tunnel mode. And we'll go ahead and exit back from here now. And we're going to go ahead and set our security association lifetime. And we're going to do it in seconds, and rather than in the amount of data in kilobytes. And here's where we have to choose the seconds. Now, is going to renegotiate a new key before this key expires, so the tunnel stays up. You wouldn't want to have it renegotiate necessarily a new key every 120 seconds. That takes router overhead when you do that. In reality, we could here, unless you've got a lot of tunnels on your router or it's a really busy router with routing protocols or something, it can handle that probably. But ideally, we don't want to make it 86,400. So here's the thing. If somebody gets the key, it's going to switch the key that often, however many seconds. So you want to get that key to switch before they get a chance to really get in there and try to use that key to start decrypting packets and can see the switches and track them. So you want to switch fairly often, but 86,400 is going to be too long. 120 is way too short. I normally do 1800 or 3600 here. We'll just do 1800. And there are some rules, like a tunnel can be built from the source peer to the destination peer, and it has to have a time of less than or the same as, less than or equal to the time on the other one, but then the other one couldn't build one back, right? So just keep these settings the same on both routers. And now we're going to have them build our crypto map. And we got to give it a name. Hey, how about we call it CCNP? Oh, and we got to tell it that it's going to, we have to give it a number, and then we have to tell it what kind it is. It's going to be IPSec ISACemp. And it's telling us here, like, hey, this ain't going to do nothing until you have an access list applied to it. So we'll go ahead and tell it match address. And we're going to match our access list, and we called that settraf. The one thing I didn't name CCNP. Okay, so now that's what tells it to match that traffic, right, in that access list, and that's what's going to tell it that that traffic belongs to this crypto map. Okay, so we also need to do a couple sets in here. Okay, one set is going to set what transform set do we want to use. Okay, so here we made a transform set and we called it CCNP. That's going to tell it to use that transform set, and then we also need to set a peer. This is going to be the outside IP of the other router. And there we go. And I think that's all we need to do. Nothing else we need to set in here. Now we can set a security association in both places. That's going to be our lifetime, but we already set that outside of the tunnel. So what happens is that one that we set outside of the crypto map is going to be the default for all crypto maps that you create. You can go and set one specifically that's different than the default if you want to. We're just going to use that. We set it as the default one for any crypto maps that get made in the future. So here's all of our stuff now. You see that we have our crypto map is set here. This is our lifetime. So if you set a lifetime within this crypto map that's different, that lifetime would show up down here. Since it's not specified, it falls back to this one. And here's a transform set. And then down here somewhere at the bottom, this is our named access list that we created to identify interesting traffic. So there's one more thing that we have to do. We have to go into the interface where we're going to encrypt that traffic from and turn on the crypto map on that interface. And now we do CCNP. And then we'll see that the IPSec comes on because now we got the crypto map on the interface. It's waiting for interest and traffic so that it can build the tunnel. So we're going to go over to the other router and we're going to do the same thing. And we start our authentication, pre-share, encryption, 3 devs. These things just need to be the same on both ends. I'd recommend using at least triple des here. Our Hyman group is going to be 1, which is really the default, but I like to set it just to be sure. Our hash is going to be MD5. And that's all the things that we have to set in here. The other thing I'll show you here is if you do show crypto IPSec policy, you can see this is the one that you created. If you have multiple policies, this would be a good idea to have these. To use this command to see if you have a policy that matches a policy on the one you're trying to build from. Okay, so we'll go ahead and do our crypto IPSec key 0 CCNP address 72.1 oh no 209.55.101.1 crypto and this is our keep alive at 1800. Okay, now we'll go ahead and build our access list. And just for fun, let's do a numbered access list here. And we'll make it 101. And it's going to be permit, IP, host, and so the destination will be 2.1.1. Okay. So the other one we did a named access list here. We're just going to do a numbered access list. And now we're ready to go ahead and do some crypto IPSec stuff. Or crypto IPSec stuff. And we'll go ahead and do our transform set. Oh, we gotta name it. So we've got that. Now we gotta set our mode to tunnel. And that's good. And so now we gotta go ahead into exit out of here 1 level. And we're ready to build our crypto map. Now we'll go ahead and do our match. And you see here we can put in our access list number. So you have to have an extended access list for the crypto map. So you can do 100 to 199, 2000 to 2699, or on the other router we did the named access list. 101. That's it. Then we're going to do a set. And here we're going to set our transform set that we're going to use, and we made it CCNP the one we created. And we're going to do our set peer a 1.1, and that's all we need there. So now we can go ahead and exit back and go to config T. Oh, I'm in config T. Go to our interface, and we'll go ahead and do crypto map CCNP. We should see our IPSec. Come on, that's always a good thing. Now, here's the thing. Since these aren't real public addresses, we know we can ping between them right now. And I'm not going to build an access list and put it on the interface to block it or whatever. So what we want to do is go ahead and do a show crypto IPSec SA. This is going to tell us some stuff. And some important stuff to know that these might be here. It's going to show you what crypto map you're using. It's going to show you the local address that crypto is on, right? The interface address. It's going to show you the current peer. This is the peer on the other end. And it's going to show you the TCP port 500. It's a good port not to block if you're doing IPSec. It's going to show you the number of packets encrypted and decrypted. This is important. We want to see these counters climb when we ping. If these counters don't increment when we ping, then that traffic didn't go through the tunnel. Okay, so we're going to do a ping of 10.1.1.1 from a source of, what type of, 10.2.2.2. And yay, the tunnel came up. We had one timeout while the tunnel was building, and the other 4 went. And so now we can do that command again, show crypto IPSec SA, and we can see that 4 packets went because the first one timed out, the other 4 went. The other place you can kind of look to verify especially if your packets aren't going out the tunnel like they're supposed to, you can do a show access list, and this was 101. You can go ahead and show your access list, and you'll see there's matches here. Now you notice that says 9 matches, and you're thinking like, why does that say 9 matches? Well, that was your pings going back and forth, but you got to remember it matches this on the inverse coming back in. So traffic when the packet returned from 10.1.1.1 to 10.2.2.2 and the other way. And so most likely, even though we see 4 packets encrypted and decrypted here, we had an extra one go out, and the access list identified it to build the tunnel, but it never came back because the tunnel wasn't timed out. And then we had 4 go successfully through that access list, both directions. So we now have our IPSec tunnel up and running like it's supposed to be. We'll go ahead and take a quick break here. Then when we come back, we're going to go ahead and build our GRE tunnel that will run within our IPSec tunnel. Okay, so now that we've got the IPSec tunnel up, we can ping between it. What we want to go ahead and work on next is getting our GRE tunnel up, and that's going to require us to create these 2 tunnel interfaces. GRE tunnels are actually extremely simple to build. When you're doing a GRE tunnel over IPSec, it's a good idea to shrink those, shrink the MTU down a little bit, just so that we don't end up with fragmentation types of issues, and because we are putting a tunnel inside of a tunnel, okay, and each of those tunnels require some packet overhead to encapsulate these packets. So let's go ahead and get started with that. I'm going to switch back over here to router 1, and actually let's go ahead and do interface, tunnel 1, I'm just going to T1. Okay, and so there's a couple things we're going to do here. First, we're going to give it its IP address. Let me move this over so I can see what the IP was. Okay, so we're going to make this one 192.1168.50.1, and there is no reason to put a whole class C on this guy because he only needs the 2 IP addresses, one for each end of the tunnel. You can essentially kind of think of this tunnel once it's built as like a point-to-point serial link. It's gonna kind of work in that same way. You're not gonna need to have more than the 2 hosts on it. So we'll give it that IP address, and then we'll go ahead and set the MTU size of the tunnel, and that's going to be IP MTU, and we're going to go ahead and set it to say 1400. And then we want to go ahead and set our TCP packet size to a little less than that, so that'll be IP TCP adjust, and then we'll set it to say 1360. Okay, so that should be fine, and now we just have to set a source and a destination for our tunnel. Now, since this is going over the IPSec tunnel, we want that destination of the GRE tunnel to be the 10222, and we want the source of the GRE tunnel to be this address here, 10111. That way, this tunnel is going across the IPSec tunnel. So we just set tunnel source 10.1.1.1, tunnel destination 10.2.2.2. Pretty simple. So now we'll just go over here to router 2, and we're going to do the same thing. This is going to be tunnel 2, IP address 192.168.50.2. Okay, and now we're going to go ahead and do our MTU adjustment. And our TCP adjustment. Oh, you see what I did? That's wrong. That should be 1400 here. Okay. And then we should go ahead and do 13, IP TCP just 1360. Okay, and now we'll do our source 10.2.2.2. That's tunnel source. And our tunnel destination is 10.1.1.1. And come back here, let that cook for a second. Yep, it comes up. So now let's go ahead and ping 192.168.50.1 source. Yeah, we're on 2. Source 192.168.50.2. And that's up. And so what I want to do again is verify those packets are going across my encrypted tunnel. So I'll do a show crypto IPSec SA. And we see we have 18 packets encrypted now that went. We'll go ahead and do that ping again. Then we'll do that show again. And 23 packets encrypted. So that's all great. We now have our traffic, our GRE tunnel built here between these 2 interfaces. So you would essentially think of these as like a virtual serial link, but in reality, they're coming across this IPSec encrypted tunnel. So now what we're going to do is go ahead and turn on some OSPF, and well, I don't want to do that. I want to go to router 1, and then go here, router OSPF 1, and then we're going to start advertising some networks here. So we'll do network 10.1.1.0.0.0.255. Oh, not EI group, folks. Got to put the area. And this is going to be area 0. And then we'll go ahead and, for our neighbor adjacency to come up, we'll also have to add the tunnel address here. You don't want to try to put this loop back. We'll come back to the drawing here. You wouldn't want to put this loop back in there because you can't do multicast directly across here between these two IP addresses, so you won't be able to build your OSPF adjacency. We want to build it here off of the GRE tunnel adapters where we can do multicast. So we'll go ahead and do network 192.168.50.0, and that's a 252 mask. So that's going to be 3. Okay, so now that half of OSPF is configured, but we do not have a neighbor adjacency yet. We'll go ahead and come over back to router 2, router OSPF 1, EI. I just got done doing the EIGRP lab. Network. Sometimes that's the hardest part on doing these labs is you get used to typing the commands from your previous one, and your finger memorizes the keystrokes before your brain can intercept. So here we want to advertise 10.22.2.0 and 0.0.0.255 area 0 and network. This one should bring up the adjacency if we did this right. And it's already up. We see that it came up right here. So now we should have some OSPF routes. So we'll do a show IP route OSPF. And there's our route to the other side. And we'll go ahead and do a show IP OSPF neighbor. We see we have a full. And the interesting thing here is on your tunnel interface, you notice you have this full dash. And you might be used to seeing full BDR, full DR, or full druther. But tunnel interfaces to OSPF look just like a serial interface does, where since there can only be 2 partners on a tunnel interface, on a GRE interface, because it's considered like a point-to-point link. Since that's the case, there can only be 2. You're only going to see that full dash. That is normal behavior for that adjacency. And show IP OSPF database. And we see that looks good. So let's just have one more little bit of fun here. What do you say? Well, let's go config t intl 222, and let's do IP address 222.2.2.2. And we'll pull a full class C mask on that guy. And let's go router OSPF1 2.2.2.2.0. And let's do this as area 2. What do you say? So now I'm going to put up a network in another area off of that loop back. And just so we can see that it advertises inter area routes right, there's no reason it wouldn't, but yeah, just have a little fun. This is what I do for fun. Let's do INTL111. And let's do IP address 111.1.1.1. And then let's go router OSPF 1. Oh, we can't be in the same area over there. Duh. Okay. Let's take that out. Let's make this. I was thinking that was area 1, but we made that one too. So we'll make this one area 1. No. Can't do that. I gotta take out the no. There we go. And here we see we have that 222 route. That's an OSPF inter-area route. Okay. And now if we do a show IP OSPF database, and our database got a little bigger. We now have, of course, some border routers. So we have some summary net link states, and looks good. So now let's go check router 2. And we now have that inter area route. And we got our summary net link states. That all looks good. And so as a final test, let's do ping 10 or 111.1.1.1 from a source of 222.2.2.2. And we're happy. Looking at the routes in the database is always great, but you always want to send that ping, make sure it really, really is working. It's possible to get a route advertised, but not have a complete path to it and back from it, like you might think that you do. So we're all good there. I mean, that's pretty much the end of the lab, just that you can see how that works. I think that might really help some people out. I know that like some phone systems and video conferencing stuff, some of the imaging softwares like the Ghost Enterprise stuff, a lot of that requires multicast, and a lot of people don't know how to make multicast work across a VPN by building a GRE tunnel. It's amazing the amount of customers I've found over the years that don't know that this simple little trick can be done. The other thing is, you know, I like to encrypt my traffic. If I have even a network where I've just got 2 routers between branches, and this is a T1, well, you know, you can set up authentication for that serial link. That's great. But, you know, especially if you're in a high-risk industry like a financial industry or something, it's a good idea to build an IPSec tunnel between these 2 guys. And that traffic is encrypted. Nobody is going to get on the wire, sniff any packets, or do anything weird. Even if they do and they get the packets, your stuff's encrypted. And then you can go ahead and build your tunnel interfaces and do all your routing and connectivity via the tunnel interfaces. And you just have these guys encrypted, especially today with MPLS networks and stuff like that. Folks, encrypt that stuff. Don't assume that your circuit is private, that it's a leased line, and so that it's secure. That is a way for hackers to find you. Encrypt at every level that you possibly can, and hopefully this little trick will help people be able to better do that. That's all I have. I'll talk to y'all later. If you have any questions, let me know. I will put a full copy, a link to where you can download this network diagram and the full copy of the configs after this lab was complete down below from my Dropbox. Just as a reference, whenever I see a lab, I like to be able to see the configs. That's all I have. I'll talk to y'all later. This is Tom with Tom Cisco Labs.